All right, good morning. For those just joining us, today is ACP review day 3. So you can either go to the fall ACP preparation folder from Power School Learning and scroll down to ACP review day 3 for everything you need. You can see what we're going over today. Attendance, there's our bell ringers, DOLs. I would open that up for today because you'll submit your answers right in there. So I'm going to kind of shrink this a little bit, but we'll do that in a second. If you're a Google Classroom user, when you go to you go to classwork, and if you scroll down within ACP preparation, you'll see it right there. ACP review day 3. That's where we are today. Okay, let me give you a moment for that, and we'll start working. So let's take a look at this bell ringer. If you remember from last class, we were talking about discontinuities. And before I show you any of these pictures, sorry, my board is going really slow. Here we go. Before I show you any of these pictures, I want to remind you down at the bottom the types of discontinuities we have. So I'll go alphabetical order. The first type of discontinuity out of the 3, I'll just put a 1 here. The first of the 3 is what we call infinite discontinuity. An infinite discontinuity, the graph will visually look like it goes up and down to infinity like this. Now, if you're using a graphing device like Desmos, it will not show you the arrows, but the graph will go off the screen both, well, I shouldn't say up and down necessarily. It could be like that, or the graph could just curve up to infinity right next to each other like this. You can have something like that as well, but typically we see it one side going up, one side going down. That happens more frequently, so I'll leave it like that. That's what we call infinite discontinuity. The graph is going to infinity at the break. So a discontinuity means there's a break in the graph. So it's no longer one piece of graph, there's multiple pieces, and the graph is at the break is going to infinity. It's created by dividing by 0, if you remember that algebraically. You divide by 0 and the factor does not cancel. Okay, the second type is in alphabetical order, jump. Now jump is a little bit different, that the graph has the same visual break, but at the break it hops from one point to another. So you'll see that it'll have like a closed dot and an open dot most frequently. Again, if there's a gap left and right, it could be 2 closed dots, but typically you'll have 1 open, 1 closed. And if you're on Desmos, you won't see the open. Just like here, you wouldn't see the arrows. On jump, you won't see an open circle, but you can see the closed circle if you have a table open as well. So that's what jump looks like. And this mathematically comes from piecewise, whenever the 2 expressions do not meet each other at the restriction value. Okay, and the third is what we call a removable discontinuity. Now, what's hard on removable or difficult is that here's what it is technically, is you have a graph and it, for the most part, looks like one piece of graph except for you have one little open circle. What's difficult is on a graphing device like Desmos, it does not automatically give you the open circle, kind of like I was saying here. So you can't see that. So it looks like just one connected piece. It looks continuous, but it's not. But we would still consider this 2 pieces just broken apart. And so I have an illustration here. If you want to look at my camera just for a second, I have this pencil and I have snapped it apart. So how many pieces of pencil am I holding right now?
2.
2. Now, no matter how hard I try, I can try to line this up perfectly and slide it together. Is it going to become 1 piece of pencil, or is it going to remain 2 pieces of pencil? See, I've kind of stuck it together. Is that now 1 piece, or is it still 2 pieces of pencil?
Still 2.
Still 2 pieces. Once I break it, it's 2 pieces. That's the idea over here with removable. Removable is 2 pieces of graph. They're pressed together, so it might look like 1 on Desmos or a different graphing calculator, but it's actually 2 pieces. Removable comes from algebraically when you divide by 0, but the factors cancel in the numerator denominator. So you could cancel them out or simplify it but that technically you're dividing by 0 at that point. So that's where they come algebraically. So let's take a look at our 4 problems and see what we come up with. Number 1, this is what we call piecewise. I have created a graph for you for piecewise. That's what this symbol refers to. So if I go to my Desmos pre-programmed graphs right there in Google Classroom and click that link, or if you're in Power School Learning, the same site that day 3 review, what we're doing today in case you've joined late. I see 5 people have joined since I started. We can go to piecewise over here. It's number 2. It has that same symbol. So I'll click this. So branch number 1 for this equation, let me slide this over, is f of x equals 3x minus 1 when x is less than or equal to 2. So that's the first branch of the branch or expression. That's what you refer to there in the equation. This would be the second branch or second expression. So I'll change this one to x squared. And this is when x is greater than 2. And so when I zoom in on this one, that is a break right there. What type of break is that? When you see the a closed dot and it doesn't show you one, which means it would be an open circle there. When it goes from one piece to another with dots, which of the 3 would that be?
A jump.
Oh, very good. So this one's a jump discontinuity. And I'm just going to say jump at x equals 2. Now, the reason they break it too is because that's where the 2 equations switch. So that's where I switch from the top expression to the bottom one graphically. This piece right here was like on the right refers to the x squared. The other one's 3x minus 1. I could prove it to you just by adding extra equations. If I said 3x minus 1, you'll see that goes through that bottom piece. Notice. And if I added an x squared, you'd see that's what goes through the right piece. It was just they switched to 2. That's where one stopped graphing and where the other started. Now, algebraically, why is it a jump? Because if you plug in the number 2, these 2 will not equal each other. So if it was continuous, what would happen is if you plugged in 2 to this side and plugged in 2 to this side, they would equal each other. So if they equal each other, they're continuous. But if they do not equal each other, then it's what we call a jump discontinuity. In this case, they're not going to be equal. 3 times 2 is 6, minus 1, I get 5. And over here, I get 4. 5 does not equal 4. That's why it's a jump discontinuity, algebraically speaking. You'll see this graph is up at 5. See, it has a height of 5. When x is 2, the y value produced 5. On this equation, when x was 2, the y value produced a 4. But again, it won't show me because it should be an open circle, but it doesn't show you that on Desmos. So that's why that one started graphing there. That would be the number 1. Now let's take a look at number 2. What types of discontinuities does each graph below contain? Well, this is now referring to just number 2. So this is not piecewise, just a normal graph. So to clear my graph, I'm going to delete these crazy letters after desmos.com/calculator. If you clear the crazy letters, it'll give you just a blank graph. Okay, so now I'm going to graph this one. J of x equals, I'm going to do the division now, x minus 2 over x squared minus 9. So here's my equation. So you know the algebra. Whenever you divide, however many powers of x you have in the denominator are typically how many breaks you're going to be. There's some exceptions to that, but you'll never have more than the power that's shown. So the most I could have here is 2, and typically we will have 2. So when you look at this break, do you see 2 breaks in this graph?
Yeah.
Yes, I do as well. So there's 3 pieces, which means they're broken twice. So we have a break here and a break there. It looks like the x values at which these break would be -1, 2, and -3, and at +3. We can check that by going to table. So go to edit list and hit this convert to table. It'll really help you out. It's like, hey, I think they're breaking at -3. And I'm just going to type in all the values so you can see it, -3, from -3 to 3. Actually, I'll go to 4 here. And you can see what happens. Desmos wish I could insert one more in here. Let's do this, -4, -3. There we go. What Desmos does is if the point is real, meaning two numbers on both sides here, it'll put a dot where the point was located. So these are the x values, -4, that one's -2, -1, 0, 1, 2, and 4. Notice it skips -3 and 3. That's because they were undefined. So that is where the breaks occur. If something is undefined, then there's a break there. So we would say, oh, by the way, I didn't even ask, what type of discontinuity is this? The graph is breaking, going down forever, up forever, down forever, up forever. What type of break is that?
Infinity.
Was it infinite, jump, or removable? I heard a voice, but I wasn't able to understand what they said.
Infinite.
Infinite, very good, Aiden. It's infinite. So this one would have infinite discontinuities. It would have two discontinuities at -3 and +3. All right. Let's check out number 3. So again, if I'm following my rules, this could have possibly 2 breaks. At most, it'll have is 2 breaks. Let's see. I'm just going to change this equation here. We'll go h of x equals x squared plus 2x over x squared minus 4. And to get the table working, I need to change this from a j to an h now. So graph. Okay. So once again, I see these points. How many breaks do you see visually?
Only one?
Only one visually. However, there's a second. Now, how do I know there's a second? It's because I looked over, I cheated, I looked at the table. How many undefineds do you see on your table?
Two.
2. So we have one at -2 and we have one at +2. That means there's a break right there at -2. You see how there's a gap in these dots? There's a break right there and right there. What type of break is this at -2? Desmos doesn't actually show it to you. Give you a hint. If you click and drag it there, the graph will do
It's
something.
a removable discontinuity.
Yeah, there you go, Joshua. It's removable. When I drag the graph there, so I'm on a point, I drag it over. Whenever I hit 2, it goes to a white circle. That's removable. So this one has a removable at -2 and another infinite at +2. So this graph would have a removable at x equals -2 and an infinite at x equals +2. And I'll show you on this one. I know I didn't show the algebra on the last problem, number 2. I did on number 1, but I did not show you the algebra number 2. I'll show you the algebra number 3. What you need to do here is factor. And this one, I can factor by GCF. It's an easier factoring. So by GCF, these both share a value of x. So I can just factor out the x. Remember, GCF is kind of like the opposite of distributing. Distributing, we multiply through a parenthesis. GCF, you divide out and create a parenthesis. So I divide out an x and it creates a parenthesis of x plus 2. So both values lost a power of x. So it went from 2 to 1, 1 to none, but I pulled the x out front. So that was GCF. On the bottom, I would have to use a different method. I'm going to use x method here. This one is saying I have 1x squared plus 0x minus 4. That's like the denominator. I'm going to use x method here. So factors of a times c, which would be 1 times -4. Oops, -4. Over b value of 0. What are factors of -4 that add up to 0? Factors of -4.
-2 and +2.
There you go, Alejandro. -2 and +2. So if I put these in parentheses, I'd have x minus 2 times x plus 2 like this. So the reason one's removable and one's infinite is because one of these cancel and the other does not. Notice I could cancel the x plus 2's, but the x minus 2 doesn't remains forever, which that one's going to become the infinite. Now, if you remember inside lies, because you would solve these as setting each one equal to 0. You're not allowed to divide by 0 in math. So the break is where it does equal 0. So you just say x minus 2 equals 0, x equals 2. That's why that one's infinite. It's because it remains forever, and infinite forever are synonyms. It's infinite at x equals 2 because of that. This one got canceled, which another word for canceled is removed. So x plus 2 equals 0 got removed, which means x would equal -2 when you solve that. And we call that one the removable. That's the algebra there. So you could apply the same concept to number 2 if you wanted to do this algebraically. You'd end up factoring this and you'd end up with x plus 3, and x minus 3 if you factor that doing x method. And since nothing cancels, they were both infinite. Okay, let's take a look now at number 4. Number 4, it says g of x, I'm going to change this to a g, equals x squared plus 2x minus 8 over x squared minus 2x. To get my table, I need to change the h to a g. And I'm looking and I see 2 undefined. That means there's 2 breaks. But when I look at the picture, I only see 1 break. And again, the maximum this could have is 2 breaks because there's only 2 powers in the denominator. I only see 1. That means it's going to be an infinite, and the one that's hidden is going to be a removable. You could just drag and look for it, but if we saw on the table, it should be at 0 and 2. So the infinite's at 0, the other is at 2, and if I go over to 2, you'll see it's an open circle. So this would also be a removable. This has an infinite at 0. And a removable at x equals 2. And again, if you want to see the algebra one more time, I'm going to factor this. The denominator is the easier one this time. They both share an x, so I'll GCF this. GCF the bottom. So if I pull out the x, I'm left with x minus 2 times x on the denominator. The numerator, I'll x method again. And so we have 1 times -8, which is -8. 1 times -8 is -8, with the 2 down below. What are factors of -8 that add up to 2?
-2 and 4.
Very good. So 4 minus 2 is 2. 4 times -2 is -8. That's it. Good work there. So it's x plus 4 and x minus 2. I just realized, oh, no, that's right. Okay, sorry. Thought I had a typo over there, but I realized, no, I don't. Okay, so this would be the removable, because algebraically it got canceled. That's the removable, and because inside lies, that's why it's x equals +2 is removable, because inside lies. This x is all alone by itself, which means it's just x equals 0. That remains forever, so it's infinite. So there's the algebra and the graphing for discontinuities.